Detecting Exoplanets, a presentation by Chloe Klimos, Angelica Sasso, Alessio Palladino, and Amanda Kronish. The human race has been trying to get concrete proof of celestial objects for thousands of years. In the past couple hundred years, astronomers have been developing impressive technology to detect a specific type of celestial object, exoplanets. Because of their small size and low brightness relative to other bodies in space, they have been challenging to find. In this presentation, we will be explaining in detail the two most successful methods for detecting exoplanets that have been used in recent years: the radial velocity method and the transit photometry method. We will also speak about their advantages and disadvantages, as well as the bias each method can produce when it comes to detecting these planets. The radial velocity method was originally one of the most frequently used methods in exoplanet detection. The RV method, also known as Doppler method, is considered an indirect way of detecting planets. This means that we are not looking for an explicit image of a planet, but the effects such an object will have on surrounding masses. In short, it uses the Doppler effect, created by the movement a star has when orbited by an object, to confirm the presence of a companion planet. The Doppler method can be dated all the way back to 1952, when Otto Struve, a Russian-American astronomer, proposed using an optical spectrometer to detect slight shifts in the star's emission and therefore changes in radial velocity. Sadly, it was deemed useless as it generated errors greater than 1,000 meters per second. In the 1990s, there were major technological advancements in the field. In 1993, the LOD spectrograph was invented in France by André Barrane. It could spot changes in a star's radial velocity as small as 7 meters per second. Using Barrane's new instrumentation, more than 700 exoplanets have since been detected. The HARP spectrograph was developed in the early 2000s and is able to identify radial velocity shifts of 0.3 meters per second. In recent years, new technology has been worked on to identify radial velocity shifts as small as 0.1 meters per second. As previously mentioned, the radial velocity method uses the Doppler effect to locate exoplanets in other solar systems. When a mass orbits a star, it exerts a gravitational tug on the star. The star then orbits a center of mass, identical to the one the object orbits. Astronomers observe the wobble the star produces, its movement to and away from Earth. To measure this wobble, they use a spectrometer, a device that can show the displacement of spectral lines created by the Doppler effect. They use this measured shift and proceed to find the radial velocity of the star. The Doppler effect is the effect of movement either to or away from an observer has on the shift of wavelengths observed by the observer. The Doppler effect is demonstrated by the following equation. V over C is equal to lambda shift minus lambda rest over lambda rest. C is the speed of light, 3 times 10 to the 8 meters per second, and V is the velocity in meters per second at which the star is moving around the center of mass. Lambda shift and lambda rest are the star's observed wavelengths when the star is undergoing a wobble and when it is at rest, respectively. To further understand this phenomenon, we must analyze two situations: a star moving away from us and a star moving towards us. A star moving away from us creates a redshift. The wavelengths we see on Earth are shifted to the red end of the spectrum. Lambda shift is larger than lambda rest. We can imagine the waves being stretched. They have to cover a larger distance as the star is moving further and further away.
On the contrary, a star moving towards us produces a blue shift. The wavelengths we see are shifted to the blue end of the spectrum, and so lambda shift is smaller than lambda rest. In this case, the waves are being compressed. They have to cover a shorter distance as the star is approaching us. The spectrometer measures the change in wavelength, and through equation 1, the star's radial velocity can be determined. If these shifts happen regularly, there is most probably an object orbiting the star. To estimate the mass of an orbiting object, the Doppler data curve must be analyzed. This graph shows the star's velocity versus time. The bigger the difference in the star's velocity, the larger the object. If the object is less than 10 times the mass of Jupiter, it is most likely a planet. Anything larger, and chances are it is another star. Larger planets, such as 51 Pegasi b, a hot Jupiter, can create a radial velocity shift of 55 meters per second, easily detectable by older spectrographs. However, smaller planets, such as Earth, only shift the radial velocity of our Sun by 0.3 meters per second and require newer and more precise instruments to be detected. The advantages of this system have made it one of the most successful tools to find new extrasolar planets. It uses simple ground-based telescopes, ones with primary mirrors as small as 2.5 meters. Such a telescope is called an Isaac Newton telescope. This method doesn't require any large, complicated professional telescopes or even anything space-based. This is beneficial financially for the institutions that are responsible for building these instruments, as they can use their resources for further research. Stars do not need to be continuously monitored with this method, as major changes in the radial velocity happen over multiple months. Luckily, a radial velocity signal is distance independent. In other words, the distance the signal must travel to reach Earth does not affect the results. This is advantageous, as this method will be able to detect gas giants a few thousand light years away. In addition, the radial velocity method is effective at detecting planets around low-mass M-type stars, as these stars are more affected by a planet's gravitational pull. This is useful, as the majority of stars in our universe are M-type stars or red dwarfs. Doppler spectroscopy also presents its fair share of limitations. A main drawback is the inability to calculate the mass of the planet. It is merely an estimation of the minimum mass the planet can have that is determined. A precise measurement of mass is important, as this is what can distinguish a large planet from a small star. Furthermore, if the star's wobble is not towards and away from Earth, any shift in wavelength will not be observed, and we would have missed the opportunity to discover a planet. This occurs when a planet's orbit is perpendicular to our line of vision. Another disadvantage is the presence of a bias when it comes to detecting planets. The method excels in finding large planets like hot Jupiters and huge gas giants, which have great gravitational effects on their stars due to their mass and small orbit. This brings the conclusion that the radial velocity method is weak at finding Earth-like planets, since the sole presence of hot Jupiters means that Earth-like planets are unlikely to have survived. Very precise instrumentation is required to find these smaller planets. Additionally, the signal-to-noise ratio, meaning the strength of the signal being analyzed to that of the surrounding interference, must be high to give accurate results. The further the star is from the Earth, the higher the chance that there will be signal interference. There's only a high degree of precision when observing stars within 160 light years from Earth. Finally, this technique cannot tell the difference between a star's wobble and basic stellar activity. Stars have hot and cold patches. When these patches come in and out of view, they can be mistaken for indications of a star's radial velocity.
The transit photometry method, known more simply as the transit method, has dominated over all other exoplanet discovery methods since the departure of the Kepler Space Telescope in 2009. Similar to the radial velocity method, the transit photometry method is an indirect way of finding exoplanets. In essence, when a planet passes in front of a star, the brightness emitted by that star decreases. This phenomenon is called a transit. The transit method has been behind the detection of over 2,700 extrasolar planets, which makes up approximately 78% of all discovered planets. This means that the transit method has been more successful than all other methods of detecting exoplanets combined. These dips in the brightness of stars can be analyzed to find the properties of the planets that orbit those stars. From Earth, we can see the transits of the two inferior planets, Venus and Mercury. The Kepler mission, which was launched in March of 2009, was one of the most effective missions in discovering new planets. It scanned over 100,000 stars in just 3.5 years and had 3,278 planet candidates, which made it by far the most successful mission of the time. By scanning so many stars simultaneously, the Kepler mission was able to transmit statistics on the number of Earth-like planets orbiting Sun-like stars. In 2018, NASA launched the Transiting Exoplanet Survey Satellite, or TESS for short, with the goal of detecting every type of planet, from Earth-sized planets to gas giants, in the 2 years that it will be orbiting. As stated previously, the transit method analyzes the dips in brightness emitted from a star when a planet passes in front of it. These changes in brightness are shown by small decreases for a fixed amount of time and for a couple of hours at a time. The change in brightness is minuscule, around 1/10,000th of the star's general brightness. If these dips happen periodically, are identical, and last for the same amount of time every time, this is strong enough evidence to conclude that an object is orbiting the star. The amount a star dims by is related to the size of the planet and the size of the star itself. A large planet orbiting a small star will lower the star's apparent brightness much more than a small planet orbiting a large star. Apparent brightness is the energy coming from a star per square meter per second. The equation for apparent brightness is B equals L over 4 pi d squared, where B is the apparent brightness in watts per meter squared, L is the luminosity of the star in watts, and d is the distance to the star from Earth in meters. As shown in this equation, the apparent brightness is proportional to the square of its distance. Therefore, the further away a star is from Earth, the lower its apparent brightness. The apparent brightness is measured using a photometer, hence the name transit photometry. In this case, a photometer is an instrument inside of a telescope that records the strength of light emitted by an object. It uses a charge-coupled device camera, or CCD camera, and registers all of the photons that reach it in its field of view. This equation for apparent brightness allows us to produce a light curve model, a graph of apparent brightness of a star versus time. A light curve model provides us with information on a planet and its orbit around its star. The time between two dips in brightness is the period of the planet's orbit. Using the fractional depth of transit, delta, in other words, how much the star dimmed by during the time of transit, we can find the following ratio. Delta is equal to Rp over Rs squared, where Rp is the radius of the planet and Rs is the radius of the star. With this equation, we can use transit photometry to find the size of the planets. It is important to note that missions like Kepler take place in space, outside of the Earth's atmosphere. The signal-to-noise ratio in transit photometry, much like for the Doppler method, needs to be high in order to give good results. The Earth's atmosphere can fluctuate and shift the light we receive from a star, even dimming it, making it harder to detect. Hence, best place to observe would be in space.
The transit photometry method comes with a large amount of advantages. It is one of the most sensitive tools used to detect exoplanets. Many types of telescopes are able to perform this task. It's great for telescopes in space, where we can observe the stars for long periods of time. While not ideal, it can also work with telescopes on the ground. Unlike the radial velocity method, this technique can determine the size of the companion planet quite precisely. When an estimation of the mass from the radial velocity method is coupled with the size of the planet measured from the transit method, we can find the density of the planet. This is particularly interesting when wanting to define what type of planet we're dealing with and get an idea about its composition. Transit photometry observations can be done on an enormous number of stars at once. This makes it highly productive and yields many results in a short amount of time. While it is great in providing the sizes of planets, transit photometry can use spectroscopy to study a planet's atmosphere. When a planet is in transit, light from the star passes through the planet's atmosphere. The spectral lines given, produced using spectroscopy, can be analyzed to determine the elements that are present. This can provide some indication as to the composition of the atmosphere. Astronomers can measure the planet's temperature by taking the star's photometric intensity before and after the planet passes behind the star. In summary, the transit method can offer us much more information about a planet than the radial velocity method can. Users of the transit method can encounter a set of difficulties as well. The main problem is the orbit of the planets. For a planet to be detected using photometry, it must pass between the observer and the star. Unfortunately, this only happens for a minority of planets. The probability of this happening in general is quite low. Sadly, many planets will go unnoticed due to this. When the orbit is not parallel with our line of sight, this can create another problem. Astronomers will only see the planet for a short amount of time, some only lasting a couple hours. This makes the chances a scientist catches a glimpse of the planet extremely low, especially when it could be years before the planet returns to transit. The last big drawback would be the relatively high number of false positives produced. Since this method focuses primarily on the size of the planets, it cannot distinguish a large gas giant from a small star. The rate of false positives can hit 40% in star systems with only one planet. We need further information, such as mass, to know if it is a planet or if it is a star. In conclusion, the radial velocity method and the transit photometry method are both unique and practical ways to detect exoplanets. The radial velocity method calculates a star's shift in the wavelength of light emitted when it is being gravitationally pulled by an orbiting planet. When these shifts happen periodically, an object is orbiting the star. Some advantages include the fact that we can use small ground-based telescopes to observe these shifts, and that we do not need to observe the stars constantly. The disadvantages are that this method is most useful to detect hot Jupiters, and that it cannot give a precise measurement of the mass of an orbiting object. The transit photometry method uses a star's dip in apparent brightness when an object passes in front of it to find orbiting planets. It is particularly valuable because it can measure the size of a planet. It can analyze thousands of stars at once and, paired with spectroscopy, can determine the composition of the planet's atmosphere. Its limitations are the high amount of false positives it can produce and the short amount of time astronomers have to see these planets once they are in transit. While these methods work great separately, we can get so much more information if we use them together.